I invite you to explore the design of audiokinetic graphics as a means to make education accessible to blind students. Students with visual impairments cannot access visual learning materials presented on slides, whiteboards, and other visual mediums. And while there exist multiple ways to represent visual information non-visually, some information cannot be adequately represented using existing approaches. Our computing technologies are actually quite limited in their ability to represent non-visual spatial information. We are especially limited in our ability to represent moving images, such as video and animation, in a non-visual format. Unfortunately, spatial information is often key to conveying information in the classroom. Many domains such as math, physics, and history rely heavily on representing spatial information. Even when a classroom teacher is discussing a poem, the teacher may rely on nonverbal cues like circling items on a whiteboard or pointing at specific messages to communicate an idea. Most, if not all, of this information is unavailable to blind students. So addressing the inaccessibility of visual content in education involves solving multiple challenging problems. First, we must identify ways to render visual content tactily. Second, we must identify ways to support the creation of non-visual content by teachers or find ways to adapt existing visual content to non-visual formats. To explore how lecture materials can be made accessible to blind students, I developed Ouija. Ouija is a hardware-software prototype that enables educators to create audiokinetic graphics. Audiokinetic graphics are tactile representations of visual content that combine audio narration with kinetic movement. Ouija allows blind students to experience audiokinetic graphics using an off-the-shelf pen plotter and the Ouija playback software. The user simply holds the robotic arm, which moves in two-dimensional space, providing a proprioceptive sense of motion. Ouija's authoring software is specifically designed to support teachers who wish to make their content accessible but lack formal training. The primary method for authoring audiokinetic graphic is through pen input using a touchscreen device and stylus, such as a Microsoft Surface tablet. Similar to a drawing application, the Ouija authoring application allows educators to sketch out lines and shapes where each stroke resembles a path of movement. The application then records the sketches along with the audio. The author may talk during their recording or may use recorded audio from another source, such as pre-recorded video lectures. The system generates the audiokinetic graphics by recording the stylus movements as timestamps and XY positions at XY millisecond intervals. Recording this data at millisecond intervals captures movements precisely, but too many XY coordinates can create jerky lines over time. Therefore, I chose to smooth the data. I first used a simple linear regression and later improved the system by calculating Bézier splines. Bézier splines are individual Bézier curves joined to form a whole curve. This data is stored in a comma-separated file. On playback, the Ouija software decodes the timestamps and coordinates. It plays back the audio and sends the coordinates as machine instructions to the pen plotter. Here's a brief example of an audiokinetic graphic.
So why does a standing wave happen and how does it happen? Well, let's say you give the end of the string here a little pluck and you cause a disturbance. That disturbance is going to move down the line because that's what waves do. It's going to come over to here. Once it meets a boundary, it's going to reflect back to the left. Now, it turns out when a string hits a boundary where it's fixed, when it hits a node, in other words, it gets flipped over. It gets reflected upside down.
To evaluate the effectiveness of Ouija at conveying non-visual content, we conducted a user study in which 18 blind individuals explored audiokinetic graphics designed for 2 lectures adapted from videos originally posted on Khan Academy. Participants cited several benefits to using audiokinetic graphics. Kinetic motion aided in understanding the lecture material by guiding the user's hand towards the content of interest. Participants expressed that it was particularly helpful to have the content presented to them rather than having to explore the tactile content to make sense of it. A participant noted, "One thing I've really struggled with is when a professor throws something on the whiteboard and I have to go find the tactile diagram, and then I'm not even sure I'm looking at the right tactile diagram because they don't describe it well." The synchronization of the audio with the kinetic motion helped participants follow the lecture content step by step. Specifically, Ouija's rapid feedback could lead to improved learning outcomes and might increase engagement in the classroom. Rapid feedback would allow students to ask questions during the lecture rather than following along behind the rest of the class. Participants also pointed out that the kinetic representations specifically helped in understanding cause and effect, which is more difficult to understand with tactile representations. The Ouija prototype represents our first attempt at building a comprehensive system for authoring, distributing, and playing audio kinetic graphics. We see several opportunities to combine Ouija's proprioceptive motion control with other tactile learning approaches and hope to further improve access to learning materials for students with visual impairments.